This is Homework Help with Jen, and we're doing Chapter 6. In the 9th edition, it's Problem 45, and in the 8th edition, it's Problem 43. All right, so I'm not going to go back up and look at what's in the book. We're just going to look at what I have written here. So first of all, they start us out with 4 moles of iron plus 3 moles of oxygen gas yields 2 moles of iron 3 oxide. And they attach to it a delta H value of negative 1,652 kilojoules for this reaction as written, this balanced equation. And they want to know how much heat is going to be released in 4 different scenarios. And what I've done is I've chosen 2 of those scenarios to do here, and using that information you should also be able to do B and C. Alright, so the first one, 4 moles of iron. This one and then B just deal with a mole quantity, so this is fairly easy actually. Okay, so 4 moles of iron, okay, and they want to know how much heat is going to be released. Okay, well, if we go up to the balanced equation in this case, we see it says 4 moles of iron. Oh, and this is 4 moles of iron. So these two numbers match. So that means that our heat released is going to match our delta H. So we could say that since delta H is negative, we're going to release 1,652 kilojoules of heat energy. That was a little bit too easy. So let me take a peek at B. And B is specifically looking at 1 mole of iron 2 oxide. I apologize for the noisy children in the background. Okay. Now, if we look up here, we see 2 moles of iron 2 oxide creates, when 2 moles of iron 2 oxide or iron 3 oxide are created, then 1,652 kilojoules of heat is released. If we only make 1 mole of iron 2 oxide, we're going to be making half this much heat. So we would take 1,652 and divide it by 2. And we will have 826 kilojoules released. They're specifically asking for a magnitude of heat released, and so I'm listing these as positive. The back of the book may list them as negative, which also indicates heat released without the word released put in. All right, now D is harder than C, so I'm skipping C. D is a limiting reactant problem. So we need to determine which is our limiting reactant first. So we will start with our 10 grams of iron. Okay. And we say, okay, well, there are 55.845 grams of iron per mole. Okay. So that means that in our 10 grams of iron, we have 0.179 moles of iron. Okay. Now we'll do this again for our oxygen. So we have 2 grams of oxygen gas, and this one I have memorized. You probably do at this point also. There's 31.998 grams of oxygen per mole. Okay. So in this, we end up with 0.0625 moles of oxygen gas. Okay, so we have 0.0625 moles of oxygen gas. All right, now we're going to compare these two numbers with 4 to 3. So our mole ratio here is 4 to 3. So we need a little bit more iron than we need oxygen. If we just look at this, we have 0.179 moles of iron, and here we have 0.0625 moles of iron. This number is a lot bigger. It's almost 3 times as big as this. Okay, we don't need 3x, we just need a little bit more. So our moles of oxygen are going to be our limiting reactant. So I'll come down here and I'll use my moles of oxygen, 0.0625 moles of O2. Now I'm going to set up a mole ratio, which says that from our equation, 3 moles of O2 yields us 1,652 kilojoules of heat. We can put the negative in there if we want to. So we say 0.0625 times 1652 negative divided by 3 is going to give me 34.4 kilojoules. Okay? Or you could say 34.4 kilojoules released. And that is thermostoichiometry.